Safest way to convert float to integer in Python? Python's math module contain handy functions like floor and ceil. These functions take a floating point number and return the nearest integer below or above it. However, these functions return the answer as a floating point number. For example, now f returns. What is the safest way to get an integer out of this float, without running the risk of rounding errors? For example, if the float is the equivalent of 1.99999, or perhaps I should use another function altogether.
All integers that can be represented by floating point numbers have an exact representation, so you can safely use int on the result. Inexact representations occur only if you are trying to represent a rational number with a denominator that is not a power of 2. That this works is not trivial at all. It's a property of the IEEE floating point representation that int-ring operator floor equals if the magnitude of the numbers in question is small enough, but different representations are possible where int, floor, 2.3, might be 1. To quote from Wikipedia, any integer with absolute value less than or equal to 224 can be exactly represented in the single precision format, and any integer with absolute value less than or equal to 253 can be exactly represented in the double precision format.
Use int, your non-integer number, will nail it. You could use the round function. If you use no second parameter, number of significant digits, then I think you will get the behavior you want. Idle output. Combining two of the previous results, we have. This converts a float to an integer fairly dependably.
That this works is not trivial at all. It's a property of the IEEE floating point representation that int floor equals if the magnitude of the numbers in question is small enough, but different representations are possible where int floor 2.3 might be 1. This post explains why it works in that range. In a double, you can represent 32-bit integers without any problems. There cannot be any rounding issues. More precisely, doubles can represent all integers between and including 253 and minus 253. Short explanation, a double can store up to 53 binary digits. When you require more, the number is padded with zeros on the right. It follows that 53 ones is the largest number that can be stored without padding. Naturally, all integer numbers requiring less digits can be stored accurately. Adding 1 to 111, omitted, 111, 53 ones, yields 100, 000, 53 zeros. As we know, we can store 53 digits, that makes the rightmost zero padding. This is where 253 comes from. More detail, we need to consider how IEEE 754 floating point works. The number is then calculated as follows, excluding special cases that are irrelevant here. -1 sign times 1 dot mantissa times 2 exponent, bias. Where bias equals 2 exponent, 1 to 1, i.e. 1023 and 127 for double single precision respectively. Knowing that multiplying by 2x simply shifts all bits x places to the left, it's easy to see that any integer must have all bits in the mantissa that end up right of the decimal point to 0. Any integer except 0 has the following form in binary. 1x, x, where the x's represent the bits to the right of the MSB, most significant bit. Because we excluded 0, there will always be a MSB that is 1, which is why it's not stored. To store the integer, we must bring it into the aforementioned form, -1 sign times 1 dot mantissa times 2 exponent, bias. That's saying the same as shifting the bits over the decimal point until there's only the MSB towards the left of the MSB. All the bits right of the decimal point are then stored in the mantissa. From this, we can see that we can store at most 52 binary digits apart from the MSB. It follows that the highest number where all bits are explicitly stored is. For this, we need to set the exponent, such that the decimal point will be shifted 52 places. If we were to increase the exponent by 1, we cannot know the digit right to the left after the decimal point. By convention, it's 0. Setting the entire mantissa to 0, we receive the following number. That's a 1 followed by 53 zeros, 52 stored and 1 added due to the exponent. It represents 253, which marks the boundary, both negative and positive, between which we can accurately represent all integers. If we wanted to add 1 to 253, we would have to set the implicit 0, denoted by the x, to 1, but that's impossible.
If you want to support the channel, please consider